people, and we can start the countdown to our next seminar at the International Institute of Physics. Okay, so welcome everybody. This is the next seminar of the International Institute of Physics, and we're very happy to welcome here today Antonio Acín from the Institute of Photonic Science in Barcelona. So I'll make a short introduction. Antonio received his PhD from the University of Barcelona. For some years, he was a postdoc in University of Geneva, and then he came back to Barcelona and joined the Institute for Photonic Science, first as a postdoc, and then later he was promoted to professor, and he stayed there until now. The field of research of Antonio is quantum information theory, and he is interested in foundations of quantum physics, in quantum optics, quantum thermodynamics, quantum communications, among others. He is a recipient of many grants and awards, prestigious grants of European Research Council, of Templeton Foundation, and Institute for Foundational Questions in Quantum Physics. In 2016, he was awarded the chair of Quantum Information Sciences by the multinational private insurance company AXA, and this is for his, in particular, for his contribution to quantum cryptography. So I also have to mention that Antonio serves as a member of the International Advisory Committee at the International Institute of Physics. So welcome home, Antonio, and unfortunately this time we cannot welcome you here in person, but I hope this will change soon. Thank you very much for accepting our invitation. Today, Antonio will talk about complex numbers and their role in quantum physics. Before I pass the word to Antonio, I just remind everybody to keep the microphones muted, and if you want to ask a question, please use raise hand feature of Zoom, or if you're in the auditorium here, you can also raise your hand. For those who joined us in YouTube, you can also ask questions in the chat. So please ask your question. We'll try to also to get that answered too. So without further ado, I pass the word to Antonio. Thank you very much again.
Okay, thank you very much. Obrigado. So I'm very happy to be giving this talk. I mean, it's a pity that I cannot be there. I've been to Natal many times in the past, and I look forward to my next visit soon. So I will now share my screen so that you can see my slides. Yes. Okay, good.
We can see you.
Okay, I see. I believe you see my slides and the pointer, so I can start. So as I was saying, thank you very much. Okay, this is when I was planning to give a talk. Usually, I tend to give talks where I put several results in the same talk, just to give an overview. But this time, I thought that I could explain this single result in a rather, say, slow way, and so that we have time to discuss if needed, and I can give you the motivation, because I think it's a result that can be of interest to many people working in quantum theory. So it's a thing of rather general, and it's mostly a result on quantum foundations, but some of the techniques we use also find an application in quantum information theory. And in fact, I mean, some of the techniques we use are very much inspired by results by Rafael Chavez in your institute, who has been pioneering the language and the techniques of quantum networks that I will be using in my talk. Okay, so this is the question we want to know. So whether complex numbers are needed in quantum theory, and we will try to understand, well, first what I mean by this question, and then what we want to understand the question. How we formalize this question in our result, and then in our work, and then the result we get. So I was discussing with Dimitri how to proceed with questions. I think, why not, if you feel that you have the need to pose a question or something is not clear, I think you should be, you shouldn't be shy, and you should ask me. Okay, I think it makes more sense, but we have time. So I'm just going to answer the question you see here. So we have time for discussion during the talk, but of course, if you prefer me to talk until the end, you can pose your question at the end of my presentation. So this is a joint, what I'm going to tell you about is a joint work that we did with Marc-Olivier Renou, who is the postdoc in my group, David Trillo, Emilia Wademan, and Acín, who are working in the group of Miguel Navasquez in Vienna. Then Armin Tabakori, who was with Nicolas Gizan. Actually, he was even master student in my group, but now is in Vienna. Well, Nicolas Gizan from Geneva and Miguel Navasquez from Vienna. So this is a question we want to address. And let's try to, I think it's a sort of interesting question, but let me try to explain you what I mean by this question. Okay, so if you think about whether complex numbers are needed in physics, I think the question, well, it's not super exciting, okay? Because in principle, I mean, when we describe a physical experiment, the description of the physical experiment is just given by the statistics we see, okay? So we do some actions on a system, and then these actions produce some outputs, okay? There are some consequences of our actions, and we describe everything by probabilities, hence real numbers. Okay, so I mean, if you think about what an experiment is, it's just this, okay? So you have a device that has some preparations, and this preparation means that you perform some macroscopic action on this, like, I don't know, you put a knob in a given position, or you put a weight again in a given position, or well, you do some macroscopic actions, and then you let time evolve, okay, and you prepare some particles, and then you do some other actions on these particles, and then you get a result. And getting a result, I mean, I will now use a language closer to quantum physics, is making a measurement. Okay, so you observe this system made in this case of two particles, and also the observation may depend on a given action. So if you think about, say, a quantum optics experiment, you may put a polarizer in a given position, and you have n different positions. So these are your n different measurements. Okay, and then as a result of this preparation and this choice of measurement, you have a result that can be a click in a given detector, or it can be that the apple falls from the tree, or you have macroscopic effects, and these are the results of your measurement. And then the description is just given by the probability. So what is the probability that I see a result R1 here and R2 here, and this R1 is just a label that we put to the result that can go from 1 to R. And the same, for simplicity, I'm taking that you can have the same number of results for the two particles. And these probabilities depend on what you prepare and which observables or which measurements you implemented. Okay, so sometimes I will use quantum language because I'm used to this, but I mean, there is nothing quantum in this description. Okay, it's just, I'm trying to describe it from a very minimalistic way, what any physical experiment is about. So these are probabilities, real numbers. I don't need complex numbers to describe this experiment. However, I mean, physics goes much more beyond describing experiments. So what we want is theories that explain the experiments. And also once the theories explain the experiments, we can even predict new experiments using this theory. Okay, so this is why we construct physical theories, because we want to understand the statistics producing experiments and we want to predict new experiments. Okay, so then we go beyond that and we invent recipes to explain the statistics we see in an experiment, and then we also can predict new probabilities that will be observed in different experiments, having different preparations and with different measurements. Okay, so if you think about quantum theory, what quantum theory tells you about the situation is that, okay, here you may have prepared p quantum states, okay, and to describe a quantum state, if I assume that the state might be mixed, it's just a density matrix. So it's a matrix in a given, acting on a given Hilbert space, and I will have p because I have p possible preparations. And I know that this state is distributed to these measuring devices, and these measuring devices I have n possible measurements with r possible results. So here I will have n possible measurements of r possible results acting on, say, the first particle of this state. And then if I assume that these are independent measurements, okay, so they take place in different locations, then I put a tensor product and I have the other set of measurements in the second device. Okay, and then quantum theory tells me that you have to define everything in terms of matrices acting on a Hilbert space. So you have the state, mix, the measurements, I combine them with the tensor product, and then you put everything together, you multiply these matrices and you compute the trace, and this gives you the probabilities. Okay, so this is the just the experiment, and this is your description within a theory of the experiment. And here you have mathematics and objects that, well, in principle, we tend to think that they are connected to reality, but you can just take them as recipes to compute probabilities. So perhaps the surprising thing is that the objects we need in quantum theory, all the objects appearing here are complex operators. So they are acting on Hilbert spaces with complex Hilbert spaces. Okay, and if you think about it, this is surprising. Okay, because before quantum theory, we never use complex numbers to construct our physical theories, because we tend to believe that, okay, even if people sometimes adopt a very practical approach and you say that these are just tools that we use to compute probabilities, and probabilities is all what matters and all what is real, our observations, well, we tend to attribute meaning to the objects we use in the theory. Okay, so when in classical physics, this is super transparent. Now we use vectors that express velocities, and we also use our coordinates to put a position. I mean, there is a very clear connection between the object we need in the theory and what happens in reality. But somehow this is not going on in quantum theory. Okay, and sometimes we have before quantum physics, we had some theories in which we use complex numbers, but it was always a matter of convenience. So I mean, in electromagnetism, we use a lot of quantum physics because we study interference effects of wave effects. Okay, and then sometimes we use the complex numbers to deal with the electric and magnetic field. But we all know that this is just a mathematical artifact that we use to simplify calculations, because I mean the electric field is real and the magnetic field is real, and the laws of electromagnetism are expressed with real quantities. Okay, so we do sometimes use complex numbers, but it's just to simplify calculations. I mean, they are not used to define the building objects of my theory. Okay, but again, if you go to quantum theory, and here I'm referring to the standard formulation of quantum theory. If you open most of the textbooks in quantum theory, then first page or page, the page where they talk about the postulates. Okay, there was a question. I don't know if I'm supposed to read the
question. James, would you like to ask your question? Microphone.
Well, I guess I could. I mean, aren't complex numbers kind of part of the formalism when we look at complex AC circuits, or we look at reflection, transmission, and absorption in optics? It's not just convenience there. Isn't that really needed?
It is not my understanding. I think, when we think about reflection, I mean, there's the electric field.
I mean, if you have absorption too, I think it has to have complex numbers.
Well, I think because you write as an exponent, maybe I don't think you need I don't remember any situation where, again, I don't think the theory is expressed in terms of complex numbers. I mean, sometimes you use them as a trick to simplify calculations. I wouldn't say so.
I mean, I think that's true.
I mean, if I think about I think about the postulates of electromagnetism, I don't think we use it. Again, I think we sometimes use them. Well, we use them sometimes for circuits when we have LC circuits, just to express the waves. No, that you have I mean, sinusoidal, cosinus, sinus, and sometimes we combine the sinus and the cosinus with an exponent with complex numbers.
But we measure complex impedances. I mean, there's an amplitude and a phase that you measure in those circuits.
Yes,
but I want to totally derail your talk, but I'm not so clear that they aren't used in other areas as well.
Sorry, they are used. What I'm saying is that the building objects of the theory, they are not phrased in complex numbers. So yeah, sure, they are used.
I'm not completely sure about that when you have absorption and things like that, but
well, I think
for reflection and transmission, I agree with you, but if you also have absorption, I'm not so clear.
Okay, my claim is that if you look at the postulates of electromagnetism, the quantities that appear there are just real quantities. Whether to make a calculation with this sometimes is convenient to add the complex numbers. Okay, maybe we can elaborate on that. I will.
Again, I'm not sure I completely agree with that, but okay. Yeah, I don't want to derail your talk, so you should go forward.
Thank you. Okay, so what is clear is that in quantum theory, the postulates appear, no? in the postulates, complex numbers appear just postulate 1. Okay, so the first thing we do in standard Hilbert space quantum theory, okay, we say that to any physical system you associate a complex Hilbert space. Okay, and then the state of this system is given by a vector in this Hilbert space. Okay, you have this postulate, and then you say that measurements are given by bases. Okay, so it's just given by some operators acting on this Hilbert space that sum up to 1. And then the Born rule tells you that once you have a state and a measurement, you should compute probabilities according to the Born rule. So you just plug them like here, or we have mixed state, you compute the trace. And then when you have different systems, you combine them according to the tensor product of the Hilbert spaces. Okay, so here, this is just standard postulates of quantum theory. And I think this is, well, I think it's the first situation in which, this is what I was saying. No? So I think if you go to the electromagnetism, for sure, I mean, Newton laws, I mean, everything is expressed in terms of real quantities. And this was something that somehow, I mean, if you want to believe that the wave function means something or has some sort of connection with reality, it's a bit weird now that I think that the wave function has to be expressed in terms of complex numbers. And I mean, we are not the first ones that we care about this question. So even Schrödinger, no, one of the founders of the theory, wrote that he didn't really like the fact that the wave function was complex, and he was even speculating about the possibility that it could be a real function. Okay, so this is more or less the motivation we had in mind. So when we say that whether quantum needs complex numbers, what we mean is if we could find quantum theory and replace complex numbers by real numbers and still have the same theory. Okay, some things will change because I mean complex and real numbers are not the same, but we would like to understand if we have a theory with the same predictive power. Okay, so the only thing we want to do is like, okay, you take the postulates of quantum theory, phrase in terms of complex Hilbert spaces, and now you just change postulate 1 and you replace by real Hilbert spaces, and then you keep everything. So you have vectors in real Hilbert spaces, measurements, you combine according to the Born rule, and you combine according to the tensor product. Okay, and again, we are not the first one considering this. I mean, this real quantum theory has been studied by several people. Like I think there is this paper by Caves and Fuchs and Rumta who were considering this version of the theory. Okay, so this is the question we want to say. I mean, does real quantum theory lead to the same experimental prediction as standard complex quantum theory? Okay, and if not, then it means that one can design an experiment in which we falsify real quantum theory. Okay, but this is something that has to be clear. So here I want to falsify this theory as phrased here. So I have to falsify any possible explanation with the real quantum theory of my experiment. And this is this will be very similar to what was done in a Bell test. Okay, I mean, in a different context. So in a Bell test, there were some theories that were postulated by Einstein, Podolsky, Rosen, these local hidden variable models or EPR theories that satisfy some conditions. And you can invent many theories that satisfy this condition. And the nice thing about Bell's theorem is that with the test, you're able to prove that none of these theories, none of these models is able to reproduce the statistics produced in a quantum experiment. So we want to do something similar. Okay, so we want to find a Bell type theorem for real quantum theory. Well, one could argue if both theories have the same predictive power, so I cannot find an experiment that I cannot explain with real quantum theory, then we could argue that the use of complex numbers is just mathematical convenience. And we could even argue that at the very end, I mean, the wave function is a real function, as Schrödinger was saying. Okay, so what I would say is that if the gap appears, then it means that in standard Hilbert space quantum theory, I need complex numbers, because if not, I mean, I lose predictive power. Okay, so wait, I will do something. Let me just, I will. Can I just keep, I'm trying, I want to do something, but I have a problem. Yes, no. I want to remove the.
What is the problem now?
I want to remove this panel here. Do you see my panel or?
No, we don't see it.
No? Okay, then it's only me. Okay, sorry. Then I go on. Sorry. Okay. Okay, so well, there is something important here is that I don't want to avoid any possible real theory with the same predictive power as quantum theory, because I think this is impossible. Okay, so I mean, even if you think in a very brutal way, there is a theory which is you just list all the probabilities that are observed in quantum experiments, and these probabilities are given in terms of real numbers. And this is a very stupid ad hoc theory, but this is a real theory that gives you the same prediction as quantum theory. Okay, the theory can be as if you do these measures, blah 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 blah. Okay, you get, I mean, and they give a real description of everything, then everything is real. Okay, so I mean, it's impossible to falsify any possible theory made of real numbers. Okay, and in fact, we have theories, say, alternative to Hilbert space quantum theory, that are phrased in terms of real numbers, like Bohm theory. Okay, and Bohm theory is expressed in terms of real quantities and the pilot wave, and it leads to the same predictions as standard Hilbert space quantum theory. So as such, I know that excluding all possible real theories with the same predictive power as quantum theory is impossible. Well, I cannot do it, and we have examples of that. So this is not what I want. I just want to exclude real quantum theory, meaning real Hilbert space quantum theory. Now, if also there is a concept with dimension. So sometimes when we explain this result to some audiences, some people knowing quantum information, they were telling us like, oh, wait, I know that there are some things that I can do in Hilbert space complex quantum theory with dimension 2 that I cannot do with Hilbert space real quantum theory of dimension 2. Sure. Okay, so this is not surprising because we understand that the complex number encodes two real numbers. So for sure, if you fix the dimension in complex quantum theory and in real quantum theory, you will find a gap. Okay, but this is not a surprise, and this is not what we want. Okay. Also, we don't want that because, I mean, we want to avoid any explanation within real quantum theory. So somehow in real quantum theory, I can play with all possible dimensions. Okay, so I expect that a spin 1/2 particle in dimension 2 complex may need a real space of dimension 4. Okay, because I mean, I need to describe a vector in dimension 2 complex, I need 4 real numbers. Okay. So dimension is not an issue. And also, if you think about it, Hilbert space dimension is not something that you measure. Okay, it's just a parameter that you assume in your description. But okay, you may think that you are measuring something of dimension 2, and actually you may be measuring something of larger dimension. Okay, so dimension is something that is a parameter that we put at hand from the outside, motivated by some experimental considerations. But I mean, there is not a way of guaranteeing that the system has a given dimension. Okay, and I think for all what I'm going to do, it's good to adopt the approach that is very similar to what happens in the Bell test, which is presenting everything as a game. Okay, so there are two people, one who is advocating complex quantum theory, and there's another one who is advocating real quantum theory. And then the complex physicist has to convince the real physicist that there is no, he cannot find an explanation for an experiment. Okay, so the complex quantum theorist is proposing experiments, and then the real quantum theorist has to find an explanation for this experiment within his theoretical framework. Okay, and well, it's like a competition. And if at some point the complex physicist finds an experiment for which the real physicist does not find an explanation, then we know the complex numbers are needed. Okay, so this has to be very important. The problem is clear, modulo the first question I had. Okay, and we'll proceed. Okay, so let's try to do the simplest we can think of. Okay, so let me just try a situation in which we have a system, a quantum system, and we make a measurement, and this system is just a matrix in this Hilbert space, and the measurement is given by other matrices in a given Hilbert space. Okay, and then what we see is the probability, and we go to the Born rule. Okay, I'm taking here mixed states just to say be more general. This is the trace of rho with the quantum state. Okay, and of course, I mean, here is the complex physicist who is trying to think of a situation in which that he could propose to the real physicist, so that say, okay, the complex physicist, she proves the real physicist to be wrong. Okay, and then the complex physicist, she expresses everything in terms of complex operators. Okay, so now the real physicist has to give another explanation for the same probabilities, but now in terms of real operators. Okay. So what he does is the following. He says like, okay, if complex dimension was D, well, probably I will need to double the dimension of my real space. So he adds a qubit here, a dimension, extra space of dimension 2. Okay. And in all my considerations, I'm going to have this extra two-dimension particle. I'm going to put it as an extra qubit, and I'm going to use these two orthogonal states, which are plus I and minus I. Okay, so these are the eigenstates of sigma y. Okay, they are orthogonal, and you can see the complex conjugate of pi I is minus I. Okay, by taking complex conjugation, you move from one state to another. Okay, so what the real physicist does, he takes the quantum state proposed by the complex physicist, and he constructs this operator. Okay, you see, this is the initial state. You make tensor product with I, and now you take the complex conjugate, because remember this was in principle a complex operator, and you make the complex conjugate with minus I. Okay, and this is a real operator, because if you compute the complex conjugate, this rho goes into rho's complex conjugate, this I goes into minus I, this goes into rho, and this goes into plus I. Okay, so since there is this symmetry, rho tilde is equal to rho tilde complex conjugate. And I play the same trick with the measurements. Okay, so I take the initial measurement proposed by the real quantum physicist takes the complex measurement and does the same trick. Okay, you take the first one, you add something multiplied by tensor multiplied by I, complex conjugate minus I. And again, this is real. And you can see that this is a valid quantum state, this is a valid measurement. This is quite easy. Okay, so now you combine everything according to the Born rule. Okay, and you can see that what you get is the same. Okay, so the probability when you compute with the real operators is the same as what you have when you compute with the complex operators. And this is basically because this number is equal to this number, which is equal to this because the probabilities are real. Okay, so no matter which experiment you can think of in this situation, I can always find an explanation within real quantum theory, and hence you cannot falsify real quantum theory, because I can always find an explanation within my theory. It might be weird, okay? You may not like it because you use a too large dimension, okay? But this is not a reason. I mean, in principle, I can always give you an explanation, which is mathematically perhaps less appealing, but it's a valid explanation within my theory. Okay, so the real quantum theory is happy. Okay, so now, also something important. I'm not saying that all states in my real quantum theory have to be of this form, okay? So they are just complex, they are just arbitrary real operators and real measurements. The only thing I'm doing is I'm giving you a recipe proving how with real operators I can reproduce an experiment with complex operators, okay? But I'm not saying that all the states in my theory have to have this form. I'm just, for me, it's for the real physicist, it's enough to identify an explanation of your experiment within the theory. And well, just, I mean, I'm not going to focus on unitary evolutions, but this also applies for a unitary evolution. Okay, so you can have an evolution of a complex space, a complex state with a complex unitary, and you can write everything as a real space with a real unitary. Okay, and with this I. Okay, so basically what it happens, somehow you split your space into the complex part and the complex conjugate, and you attach I and minus I's, so that in the end the operator you have is real, and you evolve everything with the complex evolution or the complex conjugate evolution, but the whole effect is that everything becomes real in this larger space. Okay, so this is just for the sake of completeness. I mean, I'm not going to use this. Okay, and just also note that there are other constructions that are possible. Okay, so for instance, since here you're making a single measurement on a real quantum in a complex space, you have a probability. So basically another explanation, which is very simple, is just to take another real state, which is just the classical probability. Okay, these are just orthogonal states. And you make a measurement, which is just measuring in this basis. But you can see trivially that if you apply this measurement onto this state, then you get these probabilities. Okay, I'm not going to do it, but just, I mean, since here you're making a single measurement on a real on a complex state, it's very easy. If you only work on the basis defined by the measurement, it's very easy to find another explanation within real quantum theory. Okay, just to tell you that there are different explanations of the same experiment within real quantum theory. Okay. Now you may say, well, this perhaps was too naive from the point of view of the complex physicist to think that with such simple experiment, she could falsify real quantum theory. So where do we find the key ingredient in quantum theory? We find it when we have composite systems, and then we can have things like entanglement and a Bell test. Okay, so this is where we had very successful results in falsifying other theories like EPR models. Okay, so let's try to see how we could falsify real quantum theory in a Bell test. Well, in principle, the fact that you use a Bell test doesn't mean that you are going to gain. Okay, so if you think about the paradigmatic example of a Bell inequality, this is given by what is called the CHSH Bell inequality. Well, I'm not sure if you know this Bell inequality, but it's just the standard Bell test. And it just happens that the strongest violation of this Bell test is given by this state with these measurements. Okay, and everything is real here. Okay, you have sigma z, sigma x, who are real. You have another combination of sigma s, sigma z for the two parties in a Bell experiment. So Alice, Bob, and this is the state. You see, everything is real. Everything is real. Okay, so you can have maximal violation of Bell inequalities with real operators. So, but then this is just telling you that you may be able to falsify real quantum theory in a Bell test, but not all tests are good for that. If any is good, okay, it cannot be any. Okay, so, well, we have some situations in which we can define some Bell inequalities a bit less standard than CHSH, for which to find the maximal violation that we know, you need complex numbers. Okay, so this is an inequality in which for the experts, you take some variance of CHSH. So it's like some sort of CHSH between, say, settings 1, 2 on Alice, 1, 2 on Bob, and then you have settings 1, 3 on Alice, and 3 and 4 on Bob, and settings 2, 3 on Alice, and 5, 6 on Bob. So it's a Bell test with 3 settings on Alice and 6 settings on Bob. Okay, this is for the non-experts. You won't really follow what I'm saying, but it's just another Bell inequality. And then if you try to find the maximal violation of this Bell inequality in quantum physics, you find that basically the Bell inequality violation you find is basically the one you have with qubits. And for instance, with qubits, the maximal violation is with this real state, but you need the third measurement on Alice has to be sigma y. Okay, and sigma y is complex. Okay, so this is a situation which potentially you may need complex numbers in this Bell test. Okay, so this is promising from the point of view of the complex physicist. So you say, okay, now I'm going to consider setups in which I'm preparing an entangled state of many particles, and here I'm putting 2. And these particles are distributed to different observers, and these observers make measurements. Okay, and then the complex physicist, according to the postulates of quantum theory, Hilbert space quantum theory, says that the probabilities you see are given by the trace of the state prepared here by the source, and then a measurement for Alice, tensor product, another measurement for Bob. Okay, so now you can think of many probabilities generated in this way according to standard complex quantum theory. Now it's turn for the real quantum physicist to find analogs of these objects in real quantum theory so that he can explain any probabilities that the complex quantum physicist can provide. Okay, so now you see before I was adding an extra qubit here, but now it's not clear what to do with the extra qubit. Should I send it to Alice and Bob? So the trick now is just, okay, add any qubit for any particle that is later distributed. So in this case, since I'm going to distribute 2 particles, one for Alice and one for Bob, I double the dimension of each particle that goes to every observer. So I have 1 extra qubit for this particle going to Alice and 1 extra qubit for the particle going to Bob. Okay, so I have an increase in dimension. Yes, why not? Okay, but this is valid with my game. So now I will define this rho tilde AB. So tilde will always be the real operators used by the real physicists to explain the non-tilde operators proposed initially by the complex physicists. Okay, so what I do here, I take the state I and I put the same state in this qubit. Okay, so when I do tensor product, I mean that this state is equal to plus I and this state is equal to plus I at the same time. Okay, and then I have the same here. So I combine rho and rho complex conjugate with I twice, okay, I, and with minus I twice. Now you can see that this state is real, okay, because if you take the complex conjugate, this is complex conjugate, this becomes minus I, this rho now, and this becomes plus I. So this is a valid, real, valid state in real quantum theory. And now for all the measurements, I do the same, okay? So basically, but now with a single qubit, because they receive only one qubit, okay? So I take the qubit that comes with the extra qubit that comes with the corresponding particle, and I do this trick with the measurement. So again, this measurement, this new measurement is real, okay? Because you can see it easily here. And now it's just a matter of very simple calculations to prove that if you put this measurement here for Alice, of course you define the same measurement for Bob, and you take this state and you plug everything in the Born rule, you get the same probabilities as you had here. It's just basically what I was doing before. It's simply that I is distributed and minus I are distributed to all the parties in a correlated way. So they know, all the parties know whether they should implement the initial measurement or the complex conjugate. Okay, so correlations in these extra qubits are used to synchronize the action of the parties, and then I can express everything within a real quantum theory. Okay, so this is, I mean, the intuition in the construction of the proof. So I'm saying as if at the source, you prepare this extra qubit, I and minus I, and then at the measurement, you look at this extra qubit, and depending on whether it's plus I, you apply the initial complex measurement, or whether it's minus I, you apply the complex conjugate measurement, okay? But this is just the intuition about behind this construction. Of course, once you forget about these details, you simply have here a real state that is distributed and some real measurements that are implemented. Okay, and you can forget about these I and minus I's. This is just the way, the recipe you use to map this complex explanation into this real explanation. Okay, so the real quantum theories is again happy, and this construction was, for instance, found in this paper by McKay, Mosca, and Gizan. Okay, bad. Okay, it seems that it's going to be hard. So let's now think about another setup that was, for instance, used in another no-go theorem by Pusey, Barrett, and Rudolph. Okay, so what I did was you have independent preparations of some quantum states, and you make an entanglement measurement on this preparation. Okay, so maybe this is a trick. Okay, maybe instead of using entangled state, we have to use entangled measurements. Okay, so here you have Alice, Bob, they prepare states, and you make an entanglement measurements on this state. Okay, so you have some results depending on what you measure and what you prepared. And according to quantum physics, this is just the single entanglement measurement acting on the preparation by Alice, tensor product of the preparation by Bob. Okay, when the complex quantum theories gives this to the real quantum theories, I don't have a proof, but I believe the previous construction is impossible, in which you attach an extra qubit here and here. So we didn't try hard, but I think this is impossible. This is because, I mean, when this comes here, if you follow the logic of my previous construction, here you have to implement either the initial complex measurement or the complex conjugate. But now sometimes you will have a situation in which the qubit here, the extra qubit comes in the state plus I, and sometimes comes here in the state minus I, okay? So then you don't know whether to implement the initial measurement or the complex conjugate, okay? Because this qubit is telling you, no, implement the original one, and this qubit is telling you, no, implement the complex conjugate, okay? There is a contradiction there. So this may, I believe in this configuration, you may find probabilities that you cannot explain with a model like the one I was using, okay? But, okay, this is just telling you that this type of real quantum models don't work, okay? But in real quantum theory, I'm allowed to play with any possible explanation within my theory, okay? Because I want to falsify the whole theory. And I can easily find an explanation for this experiment within real quantum theory, okay? So basically this, here you apply elements from a basis, okay? So x equal 1 means state 1, x equal 2 means state 2, x equal 3 means state 3. The same here for Bob, okay? So basically the label is encoded in the quantum state using orthogonal states. And now the measurement reads the preparation by Alice, the preparation by Bob, okay? This is just, you make the measurement in this basis. And depending on the result, you flip a coin with these probabilities, okay? So you produce the result with these probabilities depending on the measurement and the state that was prepared. And you can see that if you plug in this real, everything is real here, measurements with these real states, because I can take a real basis, then you produce the same numbers. Okay, but you see the real explanation I was using is quite different from the one I was using before, but still I'm allowed to do that because you want to find an experiment in which I cannot find an explanation. Of course, you may tell me, oh, your theory gives very different explanations for apparently similar experiments, but that's fine. Okay, so I think something that it would be nice to prove is that really adding extra qubit here, there is no way that you can explain this experiment. Okay, because here the number of extra dimensions I need to consider is very large. Okay, the dimension here grows with the number of preparations that I have. Okay, so what is the idea? Well, it seems that here I have an explanation, but it's quite different from the one I have here. Okay, so, and here I had, the difference was that I was making tensor product of measurements, and here I was making the tensor product of preparations. Well, perhaps what remains is just to use independent preparations and independent measurements. Okay, so maybe this is what I have to use to falsify real quantum theory. Okay, and this is what we try to do. Okay, so you have now the complex physicist thinks of an experiment in which you prepare independent states and you make independent measurements on these prepared independent states, including an entanglement measurement. And this is, for instance, what happens in a very seminal experiment in quantum information theory, which is entanglement swapping. Okay, so in entanglement swapping, you prepare an entangled state and you send one particle to Alice, one particle to Bob. You prepare another independent entangled state, you send one particle to Bob and another particle to Charlie. You make a measurement here, and this measurement creates non-local correlation between Alice and Charlie. Okay, so at the first step of the process, Alice and Charlie, the particles on Alice and Charlie's labs are not entangled, but as a result of this measurement, they become entangled. Okay, so what is, this is what we are going to consider. Okay, what is the explanation of this experiment in complex quantum theory? Okay, you will put a state here, tensor product another state here, you will put a measurement here, tensor product another measurement here, another tensor product another measurement here. And of course, this measurement acts on B1 and B2. Okay, and these measurements act on A, and these measurements here act on C. Okay, this is the explanation within complex quantum theory of this experiment. Now, it is possible to design an experiment in which, for all output of this measurement, Alice and Charlie violate maximally this CHSH3 inequality that require sigma y. Okay, I'm not going to explain you, but I was telling you about an inequality that for qubits requires to make a measurement in sigma y, so it requires complex measurements. And now I'm plugging this inequality in this small network, and I will look at the Bell inequality between these two parties depending on the result of this measurement, as it happens for entanglement swapping. Okay, this is what the complex experiment that the complex physicist designs. Okay, it's an experiment in which Alice and Charlie violate this CHSH3 inequality depending on Bob's result. And now the complex physicist challenges the real quantum theories to find an explanation for this experiment, for these probabilities. Okay, so now the real quantum theory does the same. Okay, I mean, he has to reason with the same postulates. Okay, so there will be a real quantum operator prepared here, another real quantum state prepared here, and real quantum measurements performed on these parties. Okay, and these things will be computed according to this. Now he has to find an explanation in terms of all these real operators that give the same probabilities as in the quantum experiment. For our proof, we can even allow these two preparations to be classically correlated. Okay, this is not so important, but we can even deal with this situation. Okay, but I mean, this is again for the experts. I mean, if you are not familiar with this quantum network language, and you can simply forget about this lambda and p lambda, and you can think that we are challenging the real quantum theories to prepare state, measurements, everything real operators in any possible Hilbert space dimension, real Hilbert space dimension, so that it gives me the probabilities that I compute here. Okay, so here again, I define a given state here, another given state here, some given measurements here, and I compute these probabilities. And this is what I give to the real quantum theories. This is the input to the problem. And now the real quantum theories has to find operators in any possible Hilbert space that combine give the probabilities. Okay. so what we prove, I mean, I don't have time to go into the details. I think it's not the purpose of this more general talk. Is that what we prove is that there is no explanation of real quantum theory for this experiment. Okay, so there are no matrices in any possible real space that you put here and here and here and here with the correct tensor products to reflect the independence in the network that reproduce the probabilities that you see when you are dealing with complex matrices. Okay, so we got what we wanted. Okay, so there is an experiment that you can explain within real quantum theory if you believe these constraints of independence. Okay, so the poor real quantum theories does not find, I mean, loses the game. Okay, so this can also be turned into a sort of Bell inequality. So basically what we do, we tested this CHSA3 inequality depending on the measurement on Bob's side, okay? And we can arrange everything into something that looks like a Bell inequality, okay, which is fine here. And then we can find that the maximum you get within real quantum theory for this expression is upper bounded by this number here. Okay, actually, we don't know whether this bound is tight. We don't know how to, in particular, we don't know how to get this value within real quantum theory. Okay, it could be that it was not tight. Okay, but we can prove that no matter in which Hilbert space you take objects in real Hilbert spaces, this quantity that we define, it's not so important, cannot be larger than 7.66. And then we prove that if you now put complex matrices, these numbers can go up to 6 square root of 2, which is around 8.5. Okay, so now you have all what you need. Okay, so we have a Bell inequality that you can test. You only need to go to the lab, check this Bell type inequality, and you find a value that is larger than 7.66. You have proven that there are experiments that you cannot explain with real quantum theory. Okay, so we're very happy. We knew that what we were proposing was not so crazy. I mean, okay, you only need to prepare 2 entangled states of 2 qubits and make here 8 qubit measurements, and here you have to make a 2 qubit measurement. But these things, I mean, quantum networks are evolving fast, so are within reach. So we were expecting someone to do it. This is when our paper appeared, but actually, perhaps we were not expecting someone to do it that fast. Okay, so we put the paper on the archive in January, and you see in March, the group of Jianwei Pan already had an experimental demonstration. Okay, so this was really impressive. Okay, only 2 months after the paper appeared, there was an experimental demonstration of our theoretical results. And actually, even we were contacted by another group, by Fan in China, and we also collaborated with them in another experiment. So in the end, the 2 experimental papers that appear a few months after in the archive, but at the very end, the 2 papers were published in the same issue of Physical Review Letters. Okay, so one after, I mean, back to back. So one is using superconducting qubits, another one is using photons. They have some drawbacks, some merits, the 2 experiments. We can discuss about them, but I think they gave a solid evidence that real quantum theory cannot explain all predictions of complex quantum theory. Okay, so at the very end, the message of my talk is quite clear and simple. Hilbert space standard quantum theory needs complex numbers. Thank you very much for your attention.
Okay, thank you very much, Antonio. We thank our speaker. And we can pass to questions. There is a question from James again. James, please go ahead.
So I haven't seen the details of your archive preprint, but I had always thought that there's a mapping. If I have a complex matrix, I can always map it onto a real matrix in twice the dimension.
Mm-hmm.
So why is it that that doesn't allow one to construct a real theory using that mapping? What is it that doesn't allow that?
Yes. So what you say is correct. So this is basically, I mean, I explained this. So what you're telling me, or what you're saying, is basically what I use here in this first explanation. Okay, so I double the dimension. Okay, and then I can express everything with real matrices. This is correct what you're saying. Okay, so things become. So the key why we can improve the result is because we are buying. Okay, let me just come back. We are defining, if you want, a specific version of real quantum theory. we are buying all the postulates of standard quantum theory, all of them, and we keep them in real quantum theory. So the only thing we do is replace here, okay? So in particular, there is something very important down here, which is the tensor product. So we combine Hilbert spaces with the tensor product. Now, if you think about real operators, the tensor product, well, if you know about, there are things like local tomography that is not possible with tensor product. But this is, you have to understand that we keep the same structure in terms of tensor products in the two theories, okay? And this is what makes, why the result works, okay? So because now if you go to the system we have, okay, yes. So again, I asked the real quantum theory to give the same probabilities, replacing everything by real operators, but without changing the tensor product structure. Okay, and this is something you cannot do, because if you try the construction you were telling me, doubling dimension and things like this, you will see that the tensor product does not is not maintained. Okay, so this is why we can prove the result. Of course, and actually there are papers. What's the name now? Stuckelberg found a version of quantum theory with real numbers, and in his version, there is like a qubit that doubles the dimension of the space, and all the parties have access to this qubit. Okay, but here, I mean, if I think of a Bell experiment, the party has only access to the part of the system that he gets from the source, but not to the rest. Okay, in a Bell test, there is a state that is prepared and sent to the parties, and party Alice only has access to what comes to her device. In Stuckelberg, this extra qubit, the double dimension, well, it's somewhere here, and all of them have to read it. Okay, so this is why in the Bell test, if I wanted to keep the causality structure, I had to send a copy of the qubit to Alice, Bob, and Charlie. You remember what I was doing in my talk, okay? So the only reason why your construction is not valid in the in my framework, okay, of course it's perfectly valid, as you say mathematically, it's because I enforce that these tensor products are maintained.
Okay, thank you.
Okay, thank you, James. I remind you that we also have a live transmission of this talk on YouTube, so there's a question from YouTube participants, and I'll slightly rephrase it. It is from Worley Campos. Worley, thank you very much for your question, and it is about particles and particle physics that have real wave functions like Majorana fermions. So do you have something to comment about this? So just maybe to remind that when we talk about fermions, there are different bases we can choose, right? We can choose to work the complex basis, or depend on dimension, or real basis. And in particular, in some dimensions, we have real representations of fermion known as Majorana fermions.
Yes.
So do you have something to comment about this in this context?
I don't think there is anything that, I'm not saying that no quantum experiment can be realified, okay, or whatever. I mean, of course, there are many situations in which I can find an explanation with real numbers, okay? So I think you should understand that the logic here is the opposite, okay? So I have a situation that I explain with complex numbers, and I fail to describe with real numbers, keeping all these tensor product structures, okay? So for me, the fact that you have some situations that you can express sometimes with complex numbers with real numbers, yes, I mean, this is perfectly valid. And indeed, I gave you all the attempts I was giving you 1, 2, and 3 were situations that we tend to explain in general with complex numbers, but I can always find an explanation with real numbers. Okay, so fourth attempt was the first situation where if I insisted to find an explanation with real numbers, I could not find it, respecting all these tensor products. So yes, I hope I answered the question. I think
it
clear.
Probably implies that Majorana fermions are not good for
exactly. Well, yes, good, yes.
For this kind of experiment. Okay,
yes.
Thank you. Well, just maybe observing the order of questions, let me let Rafael Chavez to ask the next question.
Hi, Tony. Thanks for the talk. So I actually have 2 questions, one more technical and the other more general. So let me start with the technical one. So if I understood you correctly, like it's very important that you have the entangled measurement, and at the same time, like this network structure where like the two sources are independent. But then I was a bit confused because at some point you said you could even allow for like classical correlations between the sources. And in the end of the day, you are testing a linear Bell inequality. So somehow you are putting under the rug all this network structure. So, I mean, is it really needed to have the network? Yes, or is this just some tripartite Bell scenario?
No, it's needed. It's needed. Okay, so because you have to understand that. Wait, because we already thought about this, and I had a very convincing answer now. Yes. Okay. No. Yes, but I think it will be the technique. No, it's needed. So, in a way, you can think of. Yeah, I'm not sure if I can give you a good example of that, but yeah. So, okay, I will try to. Okay, so you can think like if you have share run. Okay, so how I was mapping any quantum experiment into a real experiment before. Okay, so I was taking the original quantum experiment. I was adding this extra qubit. Okay, and then I was putting this extra qubit in the states I and minus I, which are sort of classical correlations, and I was sending this to the parties. Okay, so it seems that this shared randomness, no, I could use it to do that. Okay. Okay, but it happens that this correlated I minus I is not a valid state in real quantum theory. Okay, because you cannot mix I and minus I in real quantum theory. Okay, so I'm not sure if I'm answering your question, but it's not the same. So in principle, I'm demanding that these preparations are real. So even if you allow shared randomness, I can do more things by preparing entangled complex states here. Yeah, I don't know how to answer, but it's not the same. Yes,
this I see, but like in the end of the day, you are testing a linear Bell inequality. So somehow
yes, but well, maybe what I would say is that the extreme points, okay, are not the same in the two. Maybe because yes.
Okay. So the other question I have, it's like, so I mean, you're talking about the classical theory, like electromagnetism. I see your point that like in Maxwell's equations, like all the quantities, they are strictly real. But then this remembered me of these kind of Bell inequality violations with classical light. So I don't know if you heard of this thing before. So like basically, if you have like you can prove that Bell inequalities are also valid like for if the classical light is separable. So I mean, I'm not an expert on that, but basically you look at different degrees of freedom, and you see that if this wave function that describes your light is not separable, it's different from entanglement, but like they have this notion of separability there. If the light is not separable, like in these degrees of freedom, you can violate the sage-sage inequality. Where the terms there, it's not like an expectation value, it's more like intensity of the field. But my question is then, like, maybe you could translate this very same scenario that you have here, like with these two preparations and some entangled measurement in the center. I'm not sure what would this be in classical theory. But so my question is like, do you think that you could also prove that like a classical electromagnetism needs complex numbers? Because I mean, it seems like a direct translation from these former works to this new scenario. So have you thought about that?
Well, no, because okay, I'm to tell you the truth, I think this paper is wrong, the violation of Bell inequality with classical field. And I can tell you why, okay? Because what I do, so of course, they compute expectation values of quantity that I call A1, B1, A1, B2, A2, B1, A2, B2, and they get the same values as in quantum physics, and they get 2 square root of 2. But they make some measurements that are intensity measurements, and these measurements have infinite outputs, okay? And so they are computing a Bell inequality that is defined in a scenario with 2 measurements of 2 outputs in an experiment, we have two measurements of infinite output. Then this inequality is not an inequality for this measurement of two outputs. Okay, so they made this conceptual mistake that they were taking a quantity that can take values that go from minus infinity and infinity, and they were computing an expectation value and computing an inequality that is only valid if your outputs are plus or minus 1. So I'm not sure how much you can learn from these things.
Okay, thanks. I still have one question, but I will pass the word. No one else. No, if no one else asks something more, I have a final question. Thanks, Tony.
Thank you, Rafael. We have a question from auditorium here. So Klaus Capelli, please.
Okay. Well, Klaus Capelli here. Thank you for this very nice talk. Enjoyed it a lot. And my question is about macroscopic quantum phenomena like superconductivity. In a superconductor, the wave function becomes macroscopic, and the phase of the wave function becomes related to observables, macroscopic observables, like a Josephson current. So when I think about a Josephson junction, where two superconductors with different phases meet, and you get a current across the interface, would that be an example of your fourth attempt, which cannot be reproduced in terms of real numbers? Because the two different superconductors would be a system A and C. Or would a Josephson junction fit into one of your previous attempts, 1, 2, or 3?
Sorry, the volume was not, I had some problems with the volume. So you are talking about two junctions that prepare two different states, is that correct?
One junction between two superconductors, Josephson junction.
Okay, yes.
So would that be an example? Of course, in a Josephson junction, the phase of the wave function becomes related, becomes macroscopic, as always in a superconductor, and it's directly related to the current, the Josephson current, across the junction. Okay. So would that be an example, a condensed matter example of your fourth attempt, where the predictions of real and complex quantum mechanics are different? Or would a Josephson junction fit into one of your attempts, 1, 2, or 3?
Okay, I'm not sure. All what I can tell you is that whenever you're, so you are the complex physicist, okay? Not because you're a complex person, but because you follow the standard approach, okay? So whenever you need to put tensor products in the state preparation and the measurements, then you are in the fourth attempt. Okay, so this means that you have a state that is being some states that are being prepared. You have two sources and potentially 3 or 4. I mean, it depends on, okay, you have at least 2 sources and at least 3 measurements, I believe, okay, but at least 2 sources. Then this forces you to put tensor products for the state and for the measurements. Whenever this is the situation, you are in my fourth attempt. In all the previous cases I was considering, there was a tensor product only in the preparation, okay? So here you have a preparation, an independent preparation, and I make measurements on the 2 particles, so I cannot put a tensor product on the measurement. Or I had a single or several states that were prepared and distributed to different locations, then I only had a tensor product with the measurements, or I had measurements on a single particle. So here, what makes the distinction between all the different attempts is, say, how many tensor products you need. Okay, and I mean, tensor product is critical. Okay, so what we proved is that if you have independent measurements and independent preparations, then you can find a gap. Of course, it doesn't mean that all the situations in which I have independent preparations and measurements have a gap. Okay, but we identified one in which the gap appears. You have to understand that these proofs are difficult, okay, because you are excluding all possible explanations in real quantum theory, okay? So, I mean, what I'm saying is that there are no real matrices of, say, dimension 100 or 200 or 1,000 or 200 or 2,000 that I can put here, okay? I'm excluding all possible explanations of real quantum theory. This is why it took us a while to prove the result. I'm not answering your question, sorry, but what I'm saying is that whenever you have tensor product in the preparation, so independent preparations and independent measurements, you are in force of them. And potentially, you may be able to falsify real quantum theory. But then you have to prove it, which is not straightforward.
Okay, thank you, Klaus, for the question. Let's see, do we have any other questions? I might want to ask you maybe to explain once again, so about the experiments. So how do they in the end confirm your or compatible with your results?
Okay, so so the first experiment, okay, this is what you have to do. You have to do a standard entanglement swapping experiment. Okay, so in the first experiment, they were using superconducting qubits. So for them, they were generating 2 entangled states. So these, I forgot to mention, the entangled states you have to prepare here are the standard 2-qubit maximal entangled states. Okay, so this is simple. Here you have to make 3 measurements that are standard von Neumann measurements. Here you have to make 6 measurements that are standard von Neumann measurements, qubit measurements, okay? And here you only have to make a single measurement, which is a standard Bell measurement. Okay, this is why when we found the proof, we were very happy because it was not super crazy. Okay, you only had to prepare 2 maximum entangled states of 2 qubits, make standard projective measurements on the qubits, and here make a 2-qubit measurement. Okay, so everything seemed within reach. So in the superconducting qubit experiment, they were doing that. So they were preparing the maximum entangled state, making these measurements. Okay, so they had very good detectors. Everything was under control. I mean, it was like a quantum computation experiment where you have very good control about the gates and the states and the measurements. Now, the problem with the experiment, if you ask me, is that it was done on a very small device. Okay, so then you may say the real quantum theory may tell you, I don't believe your preparations are independent or your measurements are tensor product, because actually everything is say in the same device, and then devices talk to each other. Okay, there is no, if you want, I mean, in the most paranoid situation is things are not independent because maybe you are not even satisfying space-like considerations. But okay, so the real quantum theory may tell you, I don't think your description of the experiment is correct because the preparations are so close that there is influence, so I'm not allowed to put a tensor product. Okay, but let's say if you give some evidence for your setup, the preparations are independent and the measurements are independent, then you should describe these things with as described here in quantum theory. Okay, but let's say the main drawback was that the tensor products perhaps were not allowed. Okay, I think they were, but it's always a matter of how you feel. Okay, so I mean, in our daily life as quantum physicists, we put tensor products everywhere, but because we believe that this is a right description of the experiment, because we believe that these independence constraints are satisfied. The second experiment was a photonic experiment, so they can also prepare 2 qubit states, make these measurements. But what happens is that then you can send the photons far apart. So I think in terms of tensor products, perhaps it was cleaner. But the problem is that the detectors were not, didn't have a very high detection efficiency. And then, as in a Bell test, you may argue that there is some sort of detection loophole. Okay, so under the phase sampling assumption, you could close this loophole, but okay, there are some sort of loopholes or way outs for the real quantum theories to escape.
So in the end, what experiments showed that quantum, let's say, quantum mechanics is, sorry, complex quantum mechanics is reproduced, but you cannot explain it by real quantum mechanics.
Well, you cannot reproduce. I mean, you cannot. Yeah, there is. If you take again the theory I'm testing is the one in which I have the same postulates. I assign tensor products in the same way. The only difference that I act with real operators. This theory cannot explain all correlations in nature, because these people made the experiment independently of whether you believe in complex quantum theory. The experiment was performed. These correlations were obtained. I mean, for statistics, you don't need theories. You see them or you don't see them, okay? So these people made the experiment. They observed these probabilities, and these probabilities you cannot explain with real quantum theory.
Okay.
In experiments, you only falsify theories, okay? Like a Bell test, it's not that you prove that quantum theory is correct. Strictly speaking, what you prove is that EPR models are incorrect. So here we proved how real quantum theory can be falsified, and it was falsified.
Right. I just thought that maybe you have not exhausted all options for real theory. It's not that I'm really defending it, but
yeah, sure. This is what I said. I'm not saying that there is no real theory. Given the same bomb theory is real, and it has the same predictive power as quantum theory. But what happens in bomb theory is that you have this pilot wave that spreads everywhere, so some of the tensor product disappears. Okay.
Okay. Well, thank you very much. It was. I don't see any other questions, and it was very interesting talk and very, well, somewhat provocative idea, but I think it was quite convincing. Thank you very much, and we'll thank Antonio again.
Okay. Bye bye. Thank you.
See you all again next week in more seminars of the International Institute of Physics.
Bye bye.
Bye.
Recording